horizontal. And then you have our reaction at point B, which is equal to P over 2. Right, so we know that this is P over 2, the maximum, and the minimum is minus P over 2. So now we have determined our Vmax. Okay, so from here, from the shear force diagram, we determine that Vmax is equal to P over 2. Okay, so that is that. Then the next thing we're going to do, again, I'm going to copy the diagram. One. Okay, so I'm going to so from here we know our V. So the next thing is we need to find out our Q. Okay, so Q for the fastener, or Q. So sorry, not Q. So what Q to consider? First moment of area. Okay. Okay. Now this is the part that it requires failure analysis. Okay. Watch here. So we know that we have a shear force, which is our Vy coming down. Okay. So Vy will generate a shear flow, right? We know that the shear flow, one will go to the left and one will go to the right. Okay. And then the fastener will transmit the load to the web. Okay. So this is our member, right? Our wooden member, yes or no? All of it is made of wood. So that is our member. So what is the first moment of area will occur? Okay, which one to consider? Okay, the cross-sectional area to consider, or the cross-sectional area to consider is this area over here. Now you will say, Eugene, why that area? Because the member distribute the load. Okay, the fastener then will transmit. So you have to think of it this way. Once the shear flow occupied the entire member, okay, then it will transmit through the fastener, and then the fastener will transmit the load to the what? To the web. Okay, so that is why you take the entire area. Later on, we will do more example on this, but now just hear me out first. Okay, I repeat again, the member, right? Remember what I told you, two things. The member will distribute the load. Okay, so that's the member that's distributing the load. Okay, so after the member distribute the load, the fastener, so the fastener over here, right? The fastener over here, okay, will transmit the load to the what? To the web. Okay, so because we are calculating failure at the joints, okay, failure at the joints over here, right? We have to consider the load distribution or the shear flow distribution taken over by the member. Okay, so that's why it is that area that I hatch. That is the area that we are going to consider. Okay, so we know based on observation. I know it's a bit abstract initially, but later on, if you see me doing more examples, you get more used to it. Okay, so this is by observation. We know that this is our centroid. Okay, so this is our centroid. So we are going to do Q. Okay, so first moment of area about the z-axis. Okay, so first moment of area about the z-axis. is equal to width multiplied by depth multiplied by y bar. So the rules that I applied still stand. Okay, the first moment of area cannot cross the centroid, things like that. Okay, but that is the area where we're going to consider. So the width is 6. The depth is 4. And then the y bar is 10 plus 2. Okay, so it's 10 plus 2. That's our y bar. So the first moment of area is equal to 6 times 4 times 12 is equal to 288. It's equal to 6 times 4. Hold on. No, not 10. Hey. 10 divided by 2 plus 2. So 10 divided by 2 plus 2 times 6 times 4 is equal to 168 inches cubed. Okay, so we found our IZZ, sorry, our QZ. Okay, so now we have found our, if we look at the formula, we have found our V, we have found our Q. Next, we have to determine our I. Okay, so I about ZZ is equal to twice IZZ of the flange plus twice IZZ of the web. Okay, so while marking the term test, I realized some of you, okay, are missing some calculation for your first moment of area. Okay, so let's look at the flange first. So 6 multiplied by 4 cubed over 12 plus, this is a term that some students got missing. Okay, so because the flange centroid is not exactly, it's not on the global centroid. Okay, so this will be equal, so the distance will be 5 plus 2 squared. Okay, then plus, whereas the web, the global centroid and the web centroid are the same, you can ignore the area squared. Okay, so the width is 0.5. Then will be the depth will be 10 for 18 cube divided by 12. Let me see, 8, 10 for one side, 18 cube. Yep. So this will be equal to 6 times 4 power 3 divided by 12 plus by 6 times 4 times by 7 close bracket squared times 2 is 2416. So this is 2416 plus by 18 power 3 times 0.5 divided by 12 times 2, 486. So this is equal to 2416 plus 486 is equal to 2902 inches to power 4. Okay, let me do it again. 6 times 4 power 3 divided by 12 plus by 6 times 4 times by 7 squared times 2, 2416, 2 times 0.5 times 18 times, 2 times 1.5 times 18 power 3 divided by 12, 486 plus 2416, 2902. Okay, so we found our second moment of area. So now we can determine the force. Okay, so we know that Q is equal to is equal to P over, sorry, I want to find the Q value. The Q value that we find from the resistance is 200. Okay, so this is 200. Then this will be equal to V, which is P over 2, multiplied by the first moment of area, which is 168. And then divide by Q, divide by I is 2902. Okay, so therefore P will be equal to 200 multiplied by 2902 multiplied by 2 divided by 168. Okay? It's not difficult at all. So 200 times by 2902 times 2 divided by 168 is equal to 6909 or 690 or 6910 pound force. Okay. That the fastener or that the joints can withstand. Okay. Right. So now we know that the joints can take up to 6,910 pound of force, or P, right? We have calculated, can go up to 6,910. Okay, so this is mode 1, which is failure of the fastener. Then we are going to go to mode 2. Okay. Anyone have questions so far? I don't see anyone have question. So we are going to mode 2. So mode 2 is failure due to maximum shearing stress acting at the centroid. Okay, so we want to find the maximum stress acting at the centroid, and this is where our, by observation, this is where our centroid is. This is our centroid. So it's pretty straightforward calculation to do. So we know that the shear stress that we are, the allowable is 3 times 10 to the power 3 psi. Okay, so this is the shear stress allowable. Okay, so we know that the shear stress allowable, this is equal to Vy over Izz, right? Qz divided by T, right? So Vy, we know is equal to P over 2, right? Izz is equal to 2902 inches to the power 4. And then T, right? So the thickness, so you have thickness on one side, thickness on the other side is twice, right? 0.5. So this twice is left and right. Okay. So the only thing now we have to determine is QZ. So QZ is equal to the Q of the flange plus by Q of the web. And this one we calculated for the flange is 168 plus by the web will be twice because left and right. Then the width will be 0.5. The depth will be 5 plus 4, which is equal to 9. And this will be 5 plus 4 divided by 2. Okay, so this is our width, this is our depth, and this is our y bar. Okay, so this will give us 168 plus 9 squared divided by 2 times 0.5 times 2 is equal to 40.5. So this is equal to 168 plus by 40.5 is equal to 208.5 inches cubed. Okay, so from here we can determine our applied force due to the resistance of the structure, the shear resistance of our structure. Okay, So the shear stress of the observable is 10 times 10 to the power 3. This will be equal to Vy, which is P/2, multiplied by the Q, 208.5. Then we're going to divide by IZZ, which is 2902. And then the thickness is 2 multiplied by 0.5. So therefore, we can calculate P is equal to 3 times 10 to the power 3 multiplied by 2902 multiplied by 2 multiplied by 0.5 and then multiply by 2 again, and then divide the whole thing by 208.5. Okay. So 3 power 3 times by 2902 times 2 times 0.5 times 2 divided by 208.5 is equal to 83,511. 83.511 times 10 to the power 3 pound force. And this is expected, right? We know that the joint is the weakest, right? So this is the force that could resist due to the wooden structure under shear. So it's 83.511 times 10 to the power 3 pound force, whereas for the joint is only 6,910 pound force. And we're not done yet. So what I propose is we are going to go for a 5 minutes break. Then we come back at, we come back at 8:07. Okay, let's take a 5 minutes break.